All right, I think we are about time to start. Let's see. Oh, I got some responses to our poll. Let's see what it says here. Oh, it's a little couple of people. Well, now there's only 5 votes, so you can't take too much from that. But little nervous. Nobody's totally worried, so that's good. Um, got mostly goods. A little nervous. That's okay. The question was, how are you feeling about statics and strengths? So remember, this is a statics and strength of materials course. Um, Last time, actually, not the last video you watched, but last time we were live, we talked a little bit about the strength of material side of things, where we're talking about you put a force on an object. We use like little beams or whatever. Actually, we had some jack stands in there too. Um, and how does that object respond to those forces? And we looked at axial stress, normal stress, shear stress, tear out stress, all these different types of stresses. That was the strength of materials part. Today, mostly what we'll do is going to fall back on the static side of things again. We're going to talk about trusses. First, though, let's go and check out our web page. You know, all the Canvas materials to make sure that we're all on the same page on that. So, like I said, the last class we streamed was this class 3, where we talked about the axial stress. Then you watched a video here for stress and strain, where we combined the idea of stress and we added this idea of strain, where not only do objects experience stress, so we called stress the intensity of internal forces, but they also experience strain when they have a load applied to them. And strain is not necessarily the idea that they're about to fracture, but that the idea that they're going to deform in some way. So they're going to elongate or get shorter or something like that. So we added those two things together so that we actually created a plot. We created a stress-strain plot, and we got some material properties from that plot. Now we just made up numbers. We didn't actually go put a piece of material in a testing machine and record data, but you could do that, and that is how those tables of material properties are populated. Is somewhere along the line people have gone, taken specific samples of material, and they have done a tensile test among other tests, but a tensile test is what we were looking at, and recorded how much it stretched and how much load they were applying to it, and then they could create the stress strain plot and get things like ultimate strength and yield strength and percent elongation, things like that. They could get all these material properties from that stress strain plot. What we're doing today is, if you look here, we're on class 5, so we're going to talk mostly, almost exclusively, about trusses, but there is another topic embedded in there. I don't even think I wrote it down. Yeah, I didn't write it down, but there's another topic embedded in there that we'll need to talk about also, called moments. You'll see here that quiz 1 does open today. Again, I talked about this on Monday a little bit, but these quizzes, this one, like there's 5 of them, so quiz 1 is one of these. You have a week to work on those, but they're set for maybe 30-minute time limits, 40-minute time limits. I think this one is 30 minutes and 5 questions. So they're in the style of the exam questions, but they are on the simpler side. So they're kind of like they're a checkpoint to make sure that you are up to speed on the fundamentals of the stuff we've been talking about. So I would take them like an exam, where I sit down, I try to work them out with just my calculator. I don't go, maybe you have to look up a material property. I'm not even sure on these quizzes if you need that. But you're not, you're not trying to get a bunch of other resources. You can, if you want to, you can go look up things. You can go back and review videos or whatever. You don't have a lot of time. They are timed. But I would treat it like an exam and see how well you do based on what your understanding is. Preparing for it, I would just make sure I'm doing the homework and watching the videos, understanding them, so that you can have a good grasp of what we're talking about here. And you should do pretty well. If you do 80% or higher, then you're probably you're at least understanding the fundamentals. If you score below that, then you probably want to go back and review some of the content, ask some questions, make sure you've done the web work that's associated with that type of question, because you might be missing something fundamental that when you get to the full exam you need to know. All right. Don't see anything in the questions. Oh, we're up to 50% on 6 votes. So we're still no worried. Nobody great though. That's okay. All right. So let's go over to this idea of what I've wrote here. I've written trusses MOJ. So that's what we're going to talk about. Let's go to OneNote. First, I've got a bunch of pictures that I went on the web and looked for pictures of things that I would call trusses. So here you've got a truss bridge. We don't see too many truss bridges being built new anymore. They tend to build different types of bridges, but you still see truss bridges in existence. But that would be a truss bridge. Here you've got some roofing trusses, so somebody's building a house or something like a house, and they've built these trusses out of wood, and they're gonna soon put the roof on it. Here you've got a concert or something of some sort, and you've got trusses surrounding the stage with lights mounted on them. Here's some trusses similar to that, but they're curved. So all these others, they look, very orthogonal, but they can be curved. We are not going to deal with curved trusses in this course. We would have to approximate them more like what we've got here, where the top of this bridge looks curved, but it is really just made up of straight segments. Here's a close-up of one of the joints of a typical truss. We'll come back to that later on. Here's a truss that looks like it's part of a machine. It looks like some sort of crane type piece that's going to have a hook on the end of it, and it mounts to some other machine over here. So trusses can show up all over the place. If you look at these, you can start, if you carefully look at them, we just scanned them, but if you carefully look at these, you can start to see some of the key features that make these trusses. And so we're going to point those out. So let's write down some of the key things that make a truss a truss. Now, sometimes we can, change or, maybe not be too prescriptive with these rules, but these are the assumptions that we're going to use whenever we use these methods for analyzing trusses. So number one, well, actually, let me go ahead and say that we are talking about planar trusses for our course. So this little crane looking truss here, it is actually several trusses kind of all connected together. Each of those trusses is planar, but they're not parallel to each other. It kind of looks like they're coming to a point at the end over here where the hook would be. This bridge is 2 parallel trusses that are both planar. By planar, I mean that all the members, so a member would be one piece, like this little piece of wood right here in this wooden truss, that would be one member. So all of the members of one truss are in a single plane, would be what I mean for planar. Sometimes you would just say 2D trusses, but you can connect planar trusses together to make things like bridges and light rigs and all sorts of things. We're not really going to get into 3-dimensional trusses, although the processes that we'll use here could be applied to 3D trusses. And day 2, we talked about 3D concurrent force systems. That would also be applied to these trusses. We just have to have a couple of rules in place so that when we go to use something like MOJ, which is method of joints, that we're applying that to a truss and not to some other kind of assembly like a frame or a machine or something, which we will get to later in the quarter. All right, so number one idea for planar trusses that we need to understand, and that is that trusses are made of rigid members. And I put members in quotes because that's what we're going to call all the pieces of a truss. So like every little piece here is its own member. The best example, the clearest one of these pictures anyway, is like this one board is one member of a truss. This board from this joint to that joint, that's one member. Now, sometimes we cheat a little bit, and this board is actually all this one piece here, but a member would be from this joint to that joint. That would be one member, even if it's connected to this other one. So like I said, sometimes we're going to bend the rules a little bit, but we're going to call all the little pieces members, and they're rigid, so they're not made of a very flexible material. You know, flexible in the sense that steel can be bent or wood can be, you know, bent, but it's really rigid. All right. Number 2 is that these members that we talked about are all connected together. And remember, these are assumptions. Real world might look different, but these are our assumptions. The members are connected by frictionless pins. And I'm going to put pins in quotes because that's an important term. I guess it would be plural though in our setting here. Pins. And we're going to call those connections joints. So obviously these things do not have little pins holding everything together. In fact, in the wooden truss here, you can see these big metal plates. In this close-up thing, there are some bolts here, but that's not really a pin, like just a round bar that holds everything together. So we have to have the equivalent of this. The members are connected by frictionless pins. So what that's going to mean for us is that any one of these joints, so let's look at the one that's kind of close up here of a joint. It's going to mean that all the members are concurrent. So let's just take this one. In fact, let's just how do we want to do that? Let's copy that and put it kind of down here, and then we'll draw on top of it. So let's use this blue color. Actually, let's make it really big. All right. So there's one member, right? There's one member. We're going to ignore that one that kind of points up at the top because that's in another plane. It's going, it's not planar with these others. It's what would connect this piece to something else. So ignore that one. It does follow these same rules, but we're not dealing with 3D right now. Here's a member. There's a member. And there's a member. So all of those blue things that we shaded in, those are all truss members. Members. Or, well, that's a member. All the others are members also. So the idea is that all of these members at any joint, so remember the members are connected by pins at any joint, they are concurrent, meaning, remember that's from day one, actually, the word concurrent. So they are concurrent, meaning that all of their lines of actions will intersect at a single point. And so even though I've got this big orange plate with all these little bolts holding everything together, and there's probably some welding going on in there, the effect is still that all the members, the line of action, so line of action for this member, you know, is kind of here. Same with this member. They have the same line of action. Whoops. Here's a line of action. Here's a line of action. Here's another line of action. They all meet at this one point. So this point where everything, whoops, didn't want to erase that. The point where all of this meets is, that is the pin, and sometimes we call that a joint. That location is a joint. So even though we don't actually often have all the members held together by a physical pin, we do have the same effect of that. All right. So that was our second rule. Our third rule is that external forces, so these trusses, you know, they have to hold things up. They're a roof, or they're a bridge, or they're a crane, or whatever. They have, or they're holding up lights. They have to hold up lights, or whatever they're going to do. All the external forces on a truss are applied only at the joints. So again, the real world, there might be forces applied directly to the member, but for analyzing it as a truss, if we want to use the method of joints, method of sections that we'll talk about later, I guess next week, if we want to use those truss methods, then we have to treat it as if the forces are only applied to the joints. So what that means is, let's take none of these are super simple. Let's look at something like this wooden truss here. So let's draw something like that. It looks like it's, you know, got a member that comes down, makes a big triangle, and a couple of little triangles. Oh, that's another point. If you notice, if you look really carefully at these, all of the trusses, the planar trusses, are divided into triangles. This one's probably the easiest to see because it's all there. But you've got one big triangle, but then, now this one's cheating a little bit because it's got these weird little gusset plates. That's what these plates would be. But in general, everything's some kind of triangle. Here, there's a triangle, you know, that's a triangle. Then here's another triangle. And then off the page are more and more triangles. So trusses are divided down into triangles. And if you think about it, a triangle is, it's not able to be reshaped in any way. If I had a square, then there are enough degrees of freedom where I could physically build that square. So let me draw, we'll do that over here. If I physically built a square, so there's one side of a square, there's another side, I'm connecting them all together with frictionless pins. So if I did that, then it's not actually stable. If I were to push on it over here, then without anything breaking, you know, the truss members don't break, the pins don't break that's holding it all together, it would just, you know, it would just do something like this. You know, we just flop over. But if it's a triangle, so if I built the same thing, so same exact thing, but I triangulate it by adding one more piece in there, then when I push on it, it can't change its shape because there are no free degrees of freedom here to where it could be any other shape without breaking something. Now it could change its shape if it broke one of the pins or if it broke one of the members, but a triangle is stable. So it's got three sides, three joints, and it can't be reformed without breaking something into any other shape. So that's why all the trusses are triangulated. All right, so but let's go back to our external forces though. So external forces are applied only at joints. So we were going to draw something like this wooden truss up here. So let's draw that. So it looked like it was something where it was more or less like this. There was a member there. And let's see, I've forgotten what it looks like. Okay, yeah. Now this is not a truss yet because these pieces in the middle are not triangulated. So they have added that piece right there. So that would be here and here. So now we have a truss, we have a diagram of something like this roof truss up here. Okay. Now what our third rule is talking about, external forces applied only at the joints, means that any time I'm analyzing this using the truss analysis procedures, method of joints and method of sections, then I can only put forces, you know, at a joint somewhere. So I could do, you know, whatever I want to do with a force. I can even add multiple forces at a joint, but I can't put a force like, if I think of this as a roof truss, there's going to be a roof on top of it. I can't actually put a force here. That's not allowed. If I need that force, then I have to put it, half of it here and half of it over here. But I can't put it directly on the member and use the analysis procedures for a truss. Like in the real world, I can put a force there. I just can't use the procedures that I'm going to use today to analyze it. Okay. I couldn't hang one, couldn't hang one off of the middle there. That's not allowed in the analysis. I can do it in the real world. I just can't use the truss analysis methods to solve that problem. All right. Rule number 4. Each member only has 2 pins. So remember we said that members are connected by frictionless pins. Well, each member only has 2 pins. So if you look close enough at our actual real world truss here, this piece is probably in the real world one big long piece of lumber. But if we go to analyze it, we have to treat it as one piece here and a separate piece over here. Even if in the real world I'm going to build it as one long piece, I have to treat it like 2 separate pieces. And only 2 pins. So if I only had 1 pin on it, then it would just kind of hang there, so it's not going to do anything. That wouldn't. I guess you could do that, but it's not part of the truss. If I have more than 2 pins, that would be not counted as a truss. In the real world, like I could have this one long piece across the top or anywhere across the bottom here. It's probably all one piece, but I have to analyze it as 2 separate pieces. So for our analysis, each member has only 2 pins. And then our final one is going to require some more talking because it introduces a new term. So each member, assuming that all of this is true, made of rigid members, they're connected by frictionless pins, we've only put external forces at the joints or those pins. Each member only has 2 pins. So assuming all that's true, then each member is what we call a 2-force member. Okay, looks like I've been writing in all caps and then not in all caps, so it doesn't matter, but looks like I changed it up there. All right, each member is a 2-force member, so we need to know what a 2-force member is. So the idea and the central idea for the truss analysis methods is that ultimately I treat every piece, every member, like a 2-force member. So we need to know what a 2-force member actually is in order to do that. So I'm going to take, let's just label these. Call it that. Normally you call the joints by a letter, and you start in the bottom left and go around alphabetically. So that little piece that I just labeled AB, that would be member AB. So let's look at member AB. So I'm going to draw it as like a solid piece here. There's B, there's A. So we've kind of taken it out of the truss. So I don't remember or know how much you might recall about reaction forces at different fixtures, but the reactions at a pin so a pin I hope everybody knows what I mean for a pin. I'm just talking about something like this. So here it's going to be two different members that are connected together. And there's a physical pin that goes through everything. You know, that's what I'm talking about for a pin. It's just multiple things, usually two, but it could be more than two, that they overlap. They have a hole drilled through them, and there's a pin, like a dowel rod, that goes through that hole and holds it all together. So that's what we're talking about. So for a reaction at a pin, normally a pin, you just draw a circle or a dot or whatever. The reactions are easiest way that we're going to show pin reactions are some kind of reaction in the X direction and some kind of reaction in the Y direction. Now you could combine those together and just have a single reaction at some angle, and that'd be fine. In fact, that's what we're going to do with the two-force member. But they have two reactions. One that keeps this joint from moving left and right, so we don't let it move left and right. And one that keeps it from moving in my Y direction, which is kind of this way, because I drew it in 3D. So that pin keeps the joint stable in those two directions, but it lets things rotate if it's frictionless. You know, the way this is, this little piece up here could swing around. That'd be okay, but it can't move in any of those directions, but it could move around the pin, except there's probably other pins somewhere else in the truss holding it still. All right, so knowing that pins have two reactions, so reactions at pin, there are two reactions, and those two reactions are perpendicular to each other. Okay, so that's the rules for reactions at pin. So I've got member AB drawn over here, and if I were to draw its free body diagram, so remember, if I want to draw the free body diagram, I have to take the body, in this case member AB, separate it from all the world that it's connected to, replace any connections it had with forces, you know, reaction forces like these pin reactions, and then maybe put a coordinate system, label some stuff, angles, stuff like that. So if I did that, I'd have something that looks like this. I could just call this BY and BX. I don't really know which way they're going. So personally, when I don't know the direction that a force is going, I usually just put it in the positive direction. I think I will make an exception here and put the A going down because I know it has to oppose the B. So I would put it like that maybe. It doesn't really matter. You know, don't spend a whole lot of time trying to figure out which direction to draw a force arrow if it's not given, like it's a reaction and you're not sure. Just pick a direction and then let your equations tell you if it's positive or negative. So we'll do more and more of that if that is meaningless right now. But this is how I would draw this member. Now the problem with this is that I have 1, 2, 3, 4 things I need to solve. And if you remember some of our equilibrium equations, we might have done those last week. If you remember, we had the summation of forces in the x direction equals 0 for a part to be, or a member, or a object, a body, to be in equilibrium. We had the summation of forces in the y direction equals 0. We also had z. Summation of forces in the z direction equals 0, except we're in 2D right now, so we don't have z at all. These were our static equilibrium equations. I'm just going to shorten that so it fits. So the only two that actually are useful for us right now are these two. So I have two equations and one body with four unknowns. So that's not going to work for me because I need an equal or greater number of equations than I have unknowns. So that would be a big problem in this method that we're going to use. We're going to call it the method of joints. That would be a big problem because I'd have way too many unknowns. So what we did is we set up a bunch of rules here: rigid members, frictionless pins, joints, two pins, and they all lead to every member in a truss, assuming it has all this to be true. Every member is a two-force member. So instead of drawing this free body diagram, let's draw the free body diagram. So FBD is free body diagram. I'll go ahead and write it out this time. So let's draw the free body diagram of member AB as a two-force member. Okay, so what that lets me do is I still draw AB. But when I follow all the truss assumptions that we stated earlier, all the ones we stated earlier, then I can say that, well, if this is a two-force member, I followed all the rules, and I'm going to analyze my truss, even though it may not match the real world exactly with the external forces only at joints and all that. I'm going to only, when I draw the free body diagram, I'm only going to put the forces at joints. I'm going to make sure that everything's rigid. I'm going to make sure that I've divided all the long pieces up into individual little members. I'm going to do all that. Then I can say that this is the free body diagram for member AB. Again, I don't know if the arrows point away from it or towards it. It could be. So it could be that, or this. There's the same free body diagram, and it could be that the forces are going this way. I don't know if they are tension or compression. I might know, I might have an idea, or I might have done so many truss problems that I know which pieces are tension and compression, but, maybe I don't know. I know it's one of those two. And I know that since it's a two-force member, that the line of action, let's use green for line of action right now. So the line of action for whatever force I put has a rule on it. So the line of action is, let's say, created by connecting pin A and pin B with a straight line. So it's connect the dots between whatever the two, remember there's only two, right? Each member only has two pins. So connecting the two pins, if I connect them with a straight line, even if for some reason we did have some of these members that were curved, right? So in the curved arch looking things here, Even if they're curved, I still take the two pins and draw a straight line through them. That straight line is the line of action for the forces, the two forces. It's a two-force member on that piece. And I also know, so like, let's look at the one that I drew in tension here. I can label that as the force in member AB, and I know that this has to also be the force in member AB. So it's the same magnitude, just it's the opposite direction because it has to be in equilibrium. So if I'm pulling with 500 pounds in one direction, I've got to pull with 500 pounds in the other direction on the other end of the member so that it's not accelerating somewhere. So that's the idea for a two-force member. Okay. Now let's switch away from trusses for a little bit. Oh, I see that we got up to 60% good, 40% a little nervous. We got 10 votes. All right, so good. So we're going to switch away from trusses to a related topic, but it's broader than just trusses. So this idea is hopefully something you've seen a little bit of, but maybe not a lot. And this is the idea of a moment. Okay, so this is not specific to trusses. It is not even specific to statics, I guess, although it falls into the category of statics. If you have only taken physics courses before this, then they may not use the word moment. They might have used the word torque. So torque is the even more general term, except in engineering, we reserve torque for a very particular application, usually having to do with some kind of rotating shaft, a power transfer kind of thing. So we will talk about torque in this class, but torque and moment are technically the same thing, but in engineering we separate them into their own meanings. And we use torque in a very kind of limited sense compared to just its more general use. So earlier, day 1, day 2, actually up until now, we have had concurrent force systems. In fact, we were just talking about concurrent force systems when we were up here a little bit. We didn't really, right here with the pin joint, we've only been concurrent. So just to make sure we're all on the same page with that. So concurrent force system meant that we'd had some kind of point in the middle. Maybe it was a whole object, or maybe it's a ring, or maybe it's a pin, or who knows what it is, but we had this concurrent force system, and it had stuff connected to it, and there were forces in those things, and the line of action for everything intersected at one point. So just like we did here with the truss that looked like it was welded and bolted together, but we said it was connected by frictionless pins. Same idea there. So that was a concurrent force system. So some of what we're going to have to deal with trusses is not going to be a concurrent force system. All of the pins, so all of the pins, every one of the pins is going to be a joint that is a concurrent force system. But the entire truss is not a concurrent force system because it's a whole bunch of little concurrent force systems connected together. So the cool thing about the concurrent force system is that we had 3 equilibrium equations. And we just wrote them down, but I'll write them again. And so these 3 equilibrium equations, x, y, and z, meant that whatever body was in the center, in here I've just got a black dot, it was held stationary in the x direction, the y direction, and the z direction. But it wasn't held in like a rotational, it could spin around. Like this beam, this horizontal beam right here, you know, that could technically spin around. I even drew a little arrow there saying it could spin around the pin. So we need a little bit more. So let's take the simplest of simple trusses, which is just one beam. I don't know if that counts as a truss because it's not connected to anything, but let's just take the simplest thing. So over here, let's do non-concurrent. Oops. And we just call that a system. So here's our non-concurrent beam. So I don't know if it would count as a truss because it doesn't violate any rules, but it's just one member. So I'm going to support this with a new thing. Maybe we haven't seen this before. That's going to be called a roller. Whoops, would have two L's. And a roller, how we had the reactions at a pin, there were two reactions perpendicular to each other. A roller, let's see, where can I put that? We'll put it, can the room up here? Not really. It's like a roller skate. So it's rolling on some ground. Now I drew that as like a horizontal surface. It does not, the rollers do not have to roll on a horizontal surface. It could be at whatever angle. But the rule for a reaction for a roller, I guess I'll put it off to the side here. Is that there's only one reaction. And that one reaction is perpendicular to the surface. So in our case, I've got a roller, I just drew a little ball, and I drew a surface that's horizontal underneath that. So that would mean that there's one vertical reaction. Vertical is perpendicular to horizontal. It's a roller, so there's only one reaction. We only have one reaction because if it's like a roller skate or rollerblades, then in this configuration that I've drawn, it is not stopping this little beam, this little platform from moving left and right. It lets it do that. If I put a roller skate under a beam, it could move, horizontally. But it does keep it from moving down. And we'll usually say that it keeps it from moving up, although if it were exactly like a roller skate, you could just lift it off the ground, but we'll not worry with that right now. I'm going to show a different pin over here. I'll draw it similar to this right for now. Eventually it will become a different symbol, but for now I'll draw the pin kind of like this. So there's the pin, and it's also connected to the ground. So this setup where I have a pin and a roller holding stuff down, that's pretty common. There are other ways to use symbols to show how something's connected to the world. For trusses and for a lot of the machines and the frames and everything that we'll look at in this course, this is going to be the typical way it's connected to the world. Is there's a pin somewhere and there's a roller somewhere. So that's why I'm drawing it this way, even though it's just one beam. You can imagine this beam being, this little truss right here that we drew earlier. All right. So the thing about this is that it is possible. Why don't we, in fact, make it a truss? Let's just add a member there. We'll make it a really simple truss. So that's our little simple truss. I can put external forces at joints, so we'll put a force right there. Okay. So now, to start working on trusses, we've got this idea that every one of the members is a free body diagram, not a free body diagram, is a two-force member. They're all connected with pins. We know all this kind of stuff, but how do we get started? So typically what I have to do is I have to find out the reactions at that roller and pin, the ones that I've shown here. So to find reactions, you go and you draw a free body diagram. So a free body diagram means that I have taken my body, in this case the entire truss, taken the entire truss, isolated it from everything else, so it looks kind of like this. I'm not going to draw these in 3 dimensions now. I'm just going to draw them as straight lines. Just to simplify the drawing. So there's the free body diagram of the truss. I have replaced all the reactions that it was connected to the world. It was connected to the roller. It was connected to the pin. But I've set it free now. It's a free body. So I have to replace those connections with forces. So the roller has one force that is perpendicular to the surface it's rolling on. So that would look like this. And I could call that the, let's just say that this truss is A, B, C, D. So I could call that the reaction at A, right? Or more specifically, I could call it the reaction at A in the Y direction. The pin, if we go back up here, pins have 2 reactions that are perpendicular to each other. So the C, there would be a reaction at C in the Y direction and a reaction at C in the X direction. And then I've got this force that's hanging off of it. Let's just say that that's F. I don't need numbers right now. We'll get to a problem that actually has numbers later. So the problem here is that this little free body diagram is a non-concurrent force system, because I can't look at the left side of the page where all the lines of actions meet at a common point. If I were to draw all my lines of action here, you know, I've got this one, got that line of action, got that line of action, and I've got this line of action. So I've got like 3 different points where these lines of actions intersect, and some of them don't intersect with each other at all. Like all the vertical ones, they never intersect in a Euclidean system. So they're all parallel. So this is non-concurrent. So I have, I still have my equilibrium equations that I had before. I know that the truss is not moving in the Y direction because our whole point of this truss is that it is in a static equilibrium setting, so it's not moving anywhere. I know it's not moving in the X direction. It's not, even though I've got that roller over there at A, which would let it move in the X direction, I've also got a pin at C, which means it can't move in the X direction. So it would have to break apart for it to move in the X direction. So it can't move in X. We don't even have Z. We're just looking at a 2D thing. I'll write Z, but we're just doing 2D, so Z doesn't even show up in here. But there's one thing it could do in the current setting that I don't want it to do. And that is that technically, if the right forces acted on this thing, there's nothing that would prevent, among these 3 equations, X, Y, and Z, those equations do not prevent the truss from rotating. So for instance, if I lift it up at A, then the truss could lift up around C. I don't want it to do that. I don't want that to be an option. It could do all of that, and none of these equations would be violated. You know, it's still not moving in Y. It's still not moving in X. Like maybe an individual point is, you know, changing its X coordinate, but it's not accelerating in that direction or whatever. So I need another equation here. And that's going to be, I need to be able to say that the summation of moments about any point in the truss equals 0. Because otherwise, if I don't add that equation in there, then I am allowing the truss to rotate about some point. So I need to add that because I don't want the truss to rotate about any point. It didn't matter in the concurrent force systems because there were no forces that would even try to make it rotate. They were all just acting directly on the point itself. So that would be kind of like a door. You know, if you have a door and you push on the door hinge, then it doesn't really make the door want to open or close because that's the point about which it would normally rotate. If I push at the hinge, then it's not really going to try and make it rotate. That's the concurrent force system idea. All of my forces are pointing right at one point, and it doesn't even try to rotate that point or about that point. But now I've got forces scattered everywhere, and so if I don't have some equation that is telling me, no, this truss in the real world is not rotating about any of these points, then I leave that open. So I'm going to add this equation for non-concurrent force systems. I guess you can write it for concurrent force systems, but it just ends up saying that 0 equals 0, so it doesn't do anything. But here, I need to be able to add that. So how I do that is I need to write down, or I need to know what a moment is. We said it was a torque, but that didn't really describe it. So how a moment works in general, actually let's put it over here so I can write. A moment equals a force times a distance. Now, a couple of things with this. We're going to stick everything in our course, Engineering 220, is going to be in rectangular coordinate systems with force components in X and Y and Z. So we're not going to have vectors. So we're not going to do IJK kind of stuff. So if you were using IJK notation and vector, then there are vector math algorithms that you can use to calculate a moment. Maybe a little bit simpler than what we're going to do, but this whole course is going to be rectangular components. So X component, Y component, Z component. So just know that up front. And so how we're going to do this moment is we're going to say that moments are a force times a perpendicular distance. And so we'll have to explain that a little bit. Okay. So how I do this, I write an equation. So I write the summation of moments and I pick some point. Now, this isn't 100% true, but in general, when we're dealing with a system like this truss, where I've got a roller and a pin connecting it to the world, it's almost always, maybe like 85% of the time, the point that I'm going to sum moments about is wherever that pin is. So in our picture here, that's point C. So I would say the summation of moments about point C equals 0. And one other thing with moments is that I have to specify which way is positive. So we kind of know when we talk about X and Y that X when it goes to the right is positive, Y when it goes up is positive. That's kind of usually assumed. Or you can put a coordinate system in there with where the X-axis is and the Y-axis. So you can do that. For moments, we need to specify, is a clockwise moment positive or is a counterclockwise moment positive? Because remember, the moment is like here are we talking about, this little guy potentially spinning clockwise around that pin or counterclockwise around that pin, and which one of those is positive? So how I'm going to do that is I'm going to draw an arrow. In this case, I'll draw clockwise positive. You could do counterclockwise positive, and that'd be fine. In fact, a lot of the problems do use counterclockwise positive. All right. Hey, we got one great in the poll up there, so we're up to 9% great. All right. Let's see. So summation of moments, or let me write out how you would say this sentence here, or well, this equation. So this would translate to the summation of moments about point C is equal to 0, and clockwise moments are positive. So that's what that equation would tell us. All right. So now that I know that I don't want my trusses rotating around any point, then I can use this equation in a non-concurrent force system, and I suddenly get some more information. So let's redraw our free body diagram. Let's put some numbers on it, and let's kind of see what I'm going to do with this. Why don't we copy this guy? Copy that. I think I copied a little too much, but that's okay. All right, so we don't need that. We don't really need to label roller and surface anymore. We don't really need pin. Let's put some forces on it. Let's say that the force is 500 pounds. And we need some dimensions. So let's say that this guy is 3 feet. So is this one. And the height here is 2 feet. So it's not a giant truss. It's kind of small. But that's what we say. All right. So this is not a free body diagram because it has the pin and roller connecting it to the world. So the first thing I'm going to do if I were trying to solve this truss is I need to isolate the truss. So I'm going to draw the free body diagram of the entire truss. So that would be, again, I'm not going to draw the little lines in there. I'm just going to draw a line for a member, sort of trying to make it look like a solid piece. So there's member AB. There's BD. There's AD. There is CD. Whoops, I think I drew it too long, didn't I? It's kind of like that. And there's BC. So A, B, C, D. At D, I had 500 pounds. At C, that was a pin. So I have one reaction in the Y direction, and I have one reaction in the X direction. And at A, that was a roller. So I have one reaction that's perpendicular to the surface the roller is on. So that'll just be AY. And I had some dimensions. I had 3 feet, 3 feet, and 2 feet. And just to be totally complete, I could say that there's the x-axis and there's the y-axis. Okay, so there's my free body diagram of my little miniature truss. Okay, so the next thing I want to do after I've drawn the, and this is, again, there might be some cases where you don't follow this step, but until you know, like, oh, well, I don't need that piece of information, then this is probably what you should do until you get really familiar with solving method of joints and trusses and things like that. So I would recommend following this until you know better. All right, so that would be step 1. Draw the free body diagram of the truss. Step 2, I think we can put it over here, is find the external reactions. So for most all trusses, that's going to be the pin and the roller. Okay, so to do that, I use my free body diagram, and I have four, but I really only use 3 equations. So I have x, y, I have z, but we're only doing 2D trusses, so the z one doesn't do anything. But I've added the moment equation. Okay, so for a 2D truss, summation of forces in the z direction just says that 0 equals 0 or 1 equals 1 or whatever. So that one doesn't help me. So I really only have 3 to work with in a 2D truss. But let's write the x equation. So summation of forces in x equals 0. So I look at my free body diagram here just to the left, and the only force that I see on here is Cx. That's in the x direction. So my equation, if I add up all the forces in the x direction, I just have Cx. So Cx equals 0. So a lot of times I don't even draw it on the truss if I can just look at it and see that it is the only one in the x direction. And so I'll just go in there and just, zero it out. So it's not always 0, because there could be forces. I could have some force like that has an x component, and then Cx is not 0. But in this truss, I don't have that. Okay, so let's write another equation. Summation of forces in the y direction equals 0. Okay, here I've got AY minus 500 pounds plus CY equals 0. I've added the minus 500 because it's going in the negative y direction. It's going opposite of what I drew as positive y. So that's why I need another equation, and z is not going to help me. So, the equation. Uh-oh, we might have had a issue with our stream. Let me make sure it catches up for a second. I think it's going okay. Let me just give it a second here to catch up. Says it's okay. Might have had a little stutter there. I think it's okay. All right, I'm going to carry on, and I'll keep an eye on it. But right now it looks okay. All right. So what did I just say? I just said that we were down here. Oh yeah, the x, y, and z equations are not helping me. The z is not helping me. And so I need something else. We have recently added the idea that, well, not only do I know that this free body diagram, the one that's in the center of the screen, not only is it not moving in x, y, or z, but there's no point on this diagram that it's rotating about. So it is, I can say that the summation of moments equals 0. Now to write the equation, remember, I have to pick a particular point. So I picked C in this previous example. I have to pick a particular point. I can actually write this equation multiple times, but like I could do summation moments about A is 0, and B is 0, and C is 0, and D is 0. I could create some other point over here, E, and say that, well, the truss is not rotating about that point. So I could pick a whole bunch of stuff. Again, I'm going to say that most of the time, the best place to write the equation is wherever that pin was. So that's C. So let's write that equation. I'm going to start it, because it's a longer equation, I'm going to start it over here. So there's the equation, and I need to fill in all the stuff. So here's how the moments work. Is this equation is saying that if I imagined point C being the center of rotation for this truss, and I've got all these forces on it, AY, 500, CY, and CX, that their combined effect would be that the truss does not rotate about point C. And I said that a moment is calculated by taking a force. I have 4 of them on my free body diagram. I have AY, 500, CY, and CX, although I said CX is 0. Taking those forces individually, multiplying them times some perpendicular distance, so we need to define that, and add all that together, it should add to 0. So let's do the first one. So summation of moments about C equals 0 would say that AY, that's one of my forces, times the perpendicular distance. Now this distance is the perpendicular to the line of action of AY. So AY's line of action there. And it's measured from that line of action to whatever point I've decided I'm summing moments about. So I decided C. So the perpendicular distance between AY's line of action and point C is this distance. You know, that distance, which if I look at my diagram, it looks like it's 3 feet plus 3 feet, so it's 6 feet. All right, so AY times 6 feet is the moment of the force AY about point C. But I have to include these others too. And, does it have a positive or negative sign? So I said that clockwise moments are positive. So does the force AY, which it lost its arrowhead somehow, so there's the arrowhead on it. Does the force AY tend to make this truss want to rotate clockwise or counterclockwise about point C? So if I imagine, you know, I've got the truss right there in front of me and I push up on it at point A, it would cause that truss to go around clockwise about point C. So this gets a positive sign. Whoops, let's not write it in red though. Gets a positive sign. Okay. The next term, so I'm satisfied with AY. The next one, I'm just going left to right. So the next one is 500 pounds. It has what I would call a moment arm. So there's the line of action. And this is the perpendicular distance to point C. That, looking at my diagram, that is 3 feet. And this distance, when I talk about a force times a distance and I'm calculating a moment, I call this distance a moment arm. Okay, so we'll use that term over and over, and we'll call it a moment arm. I saw a question here. How do we decide that a moment is positive or negative? Oh, okay. So I decided just through deciding. So when you draw this arrow, or this curved arrow, that is you setting up your equation and deciding up front that all clockwise is going to be positive, or you could decide all counterclockwise are going to be positive. So initially, you choose. When you get to the equation, like I have already chosen, I've chosen that clockwise moments are positive just because that's what I wanted them to be. That's the same as choosing that, hey, X is positive when it goes to the right. You know, I could decide that no, X is going to be positive when it goes to the left, and I could write all my equations that way. So most of the time we don't do that, but you could. Or you could decide that X is positive when it goes uphill, so you could do that. That's the same thing. So you choose, and then what you do is, let's do the 500 pound. So the 500 pound here, it's going down. It's kind of getting cluttered here on my diagram, but there it is. I have drawn it. Actually, we know that that one's going down because it was part of our original diagram, right? And it's shown that it's going down 500 pounds. A and C weren't shown. I just had to pick something, and I picked that they were going up. But 500 was given to us. It is pulling down. So if I imagine that there are no other forces on the truss, and it's got a pin at C, and I pull down with 500 pounds at D, then that whole truss is going to want to, go around this way, right? That is a counterclockwise arrow about point C. So the 500 pounds about point C would have a negative sign in my equation because I said that clockwise had the positive sign, and that arrow was not clockwise, that was counterclockwise. So you have to visualize, if you isolate your one force you're dealing with in your equation, isolate that one, go to the point that you said, I said C is the point that I'm interested in. So go to that point. Does that force that I'm looking at make the object want to go clockwise or counterclockwise about that point? And then go back to your equation and say, well, I said that clockwise was positive, so I put positive signs on all the clockwise ones, and I put negative signs on anything counterclockwise. So that's how it would work. Now, I didn't ever write my 3 feet here, right? I said it, but I didn't write it. So 500 pounds times 3 feet would be the moment about point C that the 500 pound force at D creates. So moments are going to have units of foot-pounds or Newton meters or force times a distance or inch pounds. They could be a distance times a force. Let's do the last two. So CY and CX are special ones, and they're the reason why I say that usually when you're doing this, finding the external reactions for a truss, or for a lot of things, but we're talking about trusses, it's best to do this moment equation about the pin, because look at this. CY, line of action, sits right on top of the pin of C. So there's no distance. So the force times no distance is just 0. That's the same I was talking about earlier, trying to open a door by pushing on the hinge. It doesn't open or close the door at all. It doesn't do either one. So if you wanted to write it in your equation, you could write plus CY, but it's times 0 feet. So it zeroes that out. Same thing with CX. Its line of action is horizontal, so it's different. But the line of action sits right on top of C, so there's no distance. So you would have CX, I made them positive, but I guess they don't really have any sign, times another 0 feet. So these don't show up in your equation. And what that does is that now I only have one unknown in my equation. So as you get more comfortable doing this, and just through repetition, it'll be much simpler and it'll be much more intuitive what you're doing. But what I've written now is an equation I can actually solve. So rewriting, well, it equals 0, right? So rewriting the equation, it's just AY times 6 feet minus 500 pounds times 3 feet equals 0. Therefore, that little 3 dots in a triangular form, that means the word therefore. So therefore, AY equals 500 times 3 is 1,500 foot-pounds divided by 6 feet, right? Because the 6, you have to divide the 6 out on both sides. So the feet cancel out, and I actually have my calculator this time, so I can get a number easier. If I can get it to come on. 1,500 divided by 3 is, divided by 6. Whoops. 250 pounds. Okay. So a couple of things about this 250 is it came out positive. So let's scroll a little bit up. Well, didn't want to go where I want it. Well, that's fine. So since this is positive, because we could have solved the equation and we get a AY equals negative number, then that'd be okay. But since this one came out positive, then the arrow for AY in the free body diagram is correct. So that arrow is correctly drawn. It's drawn the right way. So AY really is pointing up. If we had solved all of this and we got that AY equals negative 250, then what that would mean is the arrow I drew for AY should have been drawn the other way. So that's why I was saying earlier when I was maybe, over here. I don't know which way the arrows go. It's not that big a deal. You can just let the equations tell you which way the arrow is supposed to go once you solve it. All right. Plus, now I can take this information. Oh, I drew an arrow. I can take that information and go back up to here, and now I can solve my summation of forces in the y direction equation. So taking that, I have summation of forces in the y direction equals 0. We had written AY minus 500 pounds plus CY equals 0. I just found out that AY is 250. So 250 pounds minus 500 pounds plus CY equals 0. Therefore, CY also equals 250 pounds. So now with CY, AY, and early on we had CX. With those, I've found the external reactions. Now, and it does not take nearly as long as we took. We explained every little detail. Hopefully we got all of the details across to you, but it really is much faster than that, when we actually try to solve a real problem. All of this is just getting us ready to do the method of joints. Let me see our time. Okay, we're okay. We've got a little bit of time. Let's talk about method of joints. Okay, so we were trying to solve our simple little truss here. We said that first you draw the free body diagram of the entire truss. Then you find the external reactions. And then I'm going to say probably let's redraw the free body diagram with the reactions labeled. You could go and put them on your original diagram, but for now, let's redraw free body diagram with the reactions labeled or solved. Let's say solved. Okay, so I'll cheat a little bit. I know you probably can't do this, but let's copy that, paste it in here, and we don't need all that stuff on it. So instead of CY, I've got 250 pounds. CX is 0, so that's fine. Instead of AY, I've got 250 pounds. I've got the 500 pounds on there, that's fine. And then let's just cover those blue lines up. Okay, so here's our new free body diagram. Now what I do is I'm going to pick one joint where I know at least one thing. So I have A, D, and C. I know one thing. I know there's 250 pounds pushing on A, there's 500 pounds pulling on D, and there's 250 pounds pulling on C. I don't know anything about B though, so I'm not going to pick B. So pick one joint and draw its free body diagram. Okay, so joint, this is called the method of joints. And a lot of times I write MOJ just so it's not having to write method of joints every time. All right, so it doesn't matter. You need to know at least one piece of information. At the joint you're dealing with. So let's just pick A. So I'm going to draw joint A. So not the members, just joint A. These are all frictionless pins, so there's A. We can label it A. I know that there's one external force on A, 250 pounds, I know that. That's AY that we solved a minute ago. I also know that member AB and AD are connected to joint A. I don't know their values, but a long time ago, we decided that as long as all of these rules were true, rigid members, I think that's true. Frictionless pins, we have A, B, C, D. Those we can consider frictionless pins. There were only external forces at joints. We didn't apply any forces to any members. We put them at the joints, at A, at D, and at C. Each member only had 2 pins. That was true. So that means that every member is a 2-force member, which means I can treat them like this. You know, I either know they're in tension or compression, and I know the line of action of that tension or compression is created by connecting their 2 endpoints. So I know that, you know, member AB starts out this way, and member AD starts out this way, and, you know, B is somewhere up here. You don't have to draw all these B's and D's that I'm drawing. I'm just trying to make sure that everybody's getting the same point. So the line of action for member AB is somewhere, or this is the line of action. The force is on that line of action. For AD, that's the line of action, and the force is on that line. I don't know if these are tension or compression. So again, what I normally do, if I don't know, is I just make them in the positive one, and we consider tension to be positive. So I'm going to draw that is the force in member AB, and that is the force in member AD. So I drew these in tension. FAB and FAD in tension, and I can tell they're in tension because of the way I drew them. They are in tension, or well, they are drawn in tension. They may not be in tension. They are drawn in tension because they point away from the joint, the free body diagram. They point away from the free body. In our case, the free body is just joint A or pin A. Okay. I actually know a couple of other things about this because I had some dimensions. Here they are. I knew that this angle was 3 to 2, just based on the diagrams here. Or I could calculate the angle. I could do like inverse tangent of 2 over 3 and figure out the angle between, or BAD, I could figure out that angle. I'm just going to write, for now, I'll use this little notation where it has a rise of 2 and a run of 3. That would make the hypotenuse what? The square root of 3 squared plus 2 squared, whatever that is. Let's see. 3 squared plus 2 squared. And the square root of that answer, whoops. Square root of 3 squared plus 2 squared. 3.61. We can say. Okay, we'll come back to that in a minute. All right. So now I've picked one joint, so I'm doing method joints. I have gotten joint A, and I have solved, or I haven't solved for anything, but I drew the free body diagram. So now I would treat the joint like a 2D concurrent force system. Again, you could do this in 3D, but all of the stuff we're going to do is going to be 2D. So treat it like a 2D concurrent force system, because that's what it is now. That's the whole point of method of joints and all those assumptions, is that every joint ends up being a concurrent force system. 2D or 3D, doesn't matter. We're just only going to do 2D ones. Treat the joint like a 2D concurrent force system and solve for the unknowns. So for us, that's the force in AB and the force in AD. Now it is possible that you have so many members connected to a single joint that you can't solve them. What that means is that you have what's called a statically indeterminate truss. So you can't use statics to determine all the forces. So that's not going to happen in this course. That'll be if you go on to the follow-on course. There are ways you can solve statically indeterminate trusses. You just can't use just statics. You have to use some energy methods, some other processes to get the answers if you're trying to do a statically indeterminate truss. We're just not going to do that. All right. So we've got our little free body diagram, and this is a 2D concurrent force system. So now I've got summation of forces in x equals 0, which would say FAD. The way I've got it set up would be plus FAB, but I only want the x component of AB, which would be 3 over 3.61, or you could do the cosine of whatever that angle is. What is that angle? Inverse tangent, whoops, no, not that. Inverse tangent of 2 over 3. 33.69, so 33.7 degrees. You could do FAB times cosine of 33.7 degrees. That would be the same thing as 3 over 3.61 times FAB. So however you want to do the geometry of it. This course does assume you know some trig functions and how to use them and how to get components and resultants and things like that. If you have trouble with that, then pick a method that you want to use and just use that one every time. I'll bounce back and forth between a couple of different methods, like where we just use the angles directly, or where we do like this, where we have the rise over run. So I will give multiple examples of that. You pick whatever works best for you. There are no other forces in the x direction, so this is a 0, equals 0. I can't solve it though because I don't know AD or AB. So let's write another equation. Let's write it over here. Summation of forces in the y direction equals 0. That's the only other equation I have. I have 250 pounds. That's where AY was. Plus FAB. But I only want the y component, which would be 2 over 3.61. That equals 0, and I can solve for that one. So therefore, FAB equals, let's see. I have to move that 250 to the other side, so it becomes negative. So 250 divided by 2 over 3.61. That's 3.61, not 361. So FAB looks like I get negative 451.25 pounds. So just like up here, right here, when I solved for AY, it came out positive. I knew the arrow was the right way. Here, I solve for AB and I get a negative sign. So that means that AB up here is actually supposed to be pointing towards A. So what I'm going to ask you to do is, instead of writing FAB equals negative 451, write FAB equals 451.25 pounds, and then specify that's in compression. Normally you only write C or T for tension. I'll spell it out this time. Because it's possible that when you drew your free body diagram that's on the screen here, you knew that it was going to be in compression, and you just went ahead and drew that arrow pointing towards A, which would make it a compressive arrow. And so then yours would come out positive, and positive wouldn't mean tension to you. It would have meant compression. So it's better when you're doing these member forces to write the magnitude, and then after that, instead of relying on plus and minus, write, well, I didn't mean to move the L, write tension or compression. So you don't have to spell out the word, write T or C, so that there's no confusion on if it's tension or compression. And now we can take AB, plug it back into here, and solve this equation. So FAD plus, here's where you got to be careful, because how do you put compression in here? You know, you can't put a word into this equation. So I really need to put the negative sign here, because this FAB, I calculated it according to my free body diagram as a negative 451.25 pounds. So you have to be careful with the when you go and substitute in the plus and minus signs. It is doable, but you do have to be careful that you're putting the correct sign on something. That's kind of why I went and wrote this plus sign, because my diagram shows it as a plus X component, right? It's going to the right. But my value I calculated based on my diagram is actually a negative number. So that's why I did it that way. It'll take you some time, a couple of iterations to make that easy in your mind. But it will get better the more often you do it. And some of you, it might just be, well, that's obvious. So I do have to multiply this by 3 over 3.61 to only deal with the X component. So this looks like it's going to say 451.25 times 3 divided by 3.61. I need to move that. That's all negative. I need to move it to the other side so it becomes positive. So therefore, FAD is a positive 375 pounds. Again, I don't want to leave it as just positive or negative, though, because they can mean different things depending on how I drew the original diagram. So I really want FAD equals 375 pounds of tension. Okay, I think we're going to do more of this. Next time is more trusses. Actually, it's only trusses. So I think that's probably a good stopping point. We didn't solve all the truss, except that if you notice, this truss is symmetric. The dimensions are symmetric. The forces are symmetric. So I do know, just by symmetry, that CD is equal to AB. So they have the same force, same magnitude. CD, or I might have said that wrong. CB is equal to AB. CD is equal to AD. Those are, by symmetry, they're the same. I don't know what BD is. We'd have to come back to that. Actually, I do know what it is, but it's 500 pounds. But that's because it's a special case. And you'll get more familiar with those as you go along. The idea would be that you start back, let's see. Oh, right here. No, that's the entire, you don't have to do that again. You would start back at number 4. You would pick a new joint, B or D or C, and go through method of joints again for that joint until you've solved all the stuff you need to solve. So that would be the idea with method of joints. And we'll do some more problems. I have some web work opened up that you can practice on these. They start out relatively simple and then they get more and more elaborate. And you will have these on exam 1, of course. I don't think they're on the quiz 1. So quiz 1 I don't think has any trusses. It's just the stresses we've already done. Maybe a concurrent force system. But we'll come back on Monday and we'll pick up with trusses and we'll do some more elaborate ones. We'll do another method. So we'll add method of sections to our method of joints. Still in the context of trusses though. So hopefully, I don't see any other questions pop up in the chat over here. So we're going to close down and we'll come back Monday. Make sure you've got your web work. It's starting to close now. So homework 1 is closed. So make sure that you're keeping up with it. Don't get too far behind on that. You may have also noticed an OP1. That is optional. I'm going to add a CH1, which is challenging. The optional ones are just extra practice. So you do them for extra practice. The challenging ones, so there'll be a CH1. Those, if you complete those, they're extra credit. So you can actually get some extra, maybe you missed some problems in the regular web work. You've done some of the challenging ones so they can offset a little bit. So I haven't opened those up yet. The optional ones they're just extra practice though. You don't get any extra credit for doing those. All right. I will see you all on Monday. I'm going to go open up the challenging problems. I'll look for any Discord or email messages. We can do Zooms. I don't have that many time slots for Zoom, but if you have a particular question that nothing else is answering, then we can do a Zoom to try and figure out the answer. All right, I will see y'all on Monday.